Okay, next I'm going to illustrate the main ideas behind the proof of this log drop property. Okay, let's first review the symbols. Okay, Q is the query point, and P circle, which I abbreviate as P from now on. Okay, so no more P circle. All right, so I'll call P circle just P. So P is the point that you are currently standing at. Okay, so that's the point um, that is being visited by the greedy algorithm. Okay, and P plus, this P plus L, right? So no more P plus L. I will use P plus for short. Okay, so this P plus is the best L neighbor of P. Okay, best L neighbor of P. Okay, so in other words, this is the next hop by greedy. Okay, so here this P star is the nearest neighbor of Q. Okay, so 3 points here. Okay, several points here. Now I want to prove to you that either this P plus is something returnable, which means this is a 1 plus epsilon ANN of Q. Okay, either this is true, or the distance of this P plus to P star. Okay, so P star is sort of the destination, right? So the distance to the destination is significantly less than the distance uh, from P to P star. Well, I said significantly less. I should be more careful about that. What I really want to show is this relationship. Okay, as you can see, this inequality here. Now pay attention to the ceilings here. Okay, so we will uh, unfold this bit by bit. So this is the log drop property, right? So this is a very important property because I have already explained that this property guarantees that the proximity graph is query efficient. Okay. So before I show you the entire proof, let me first give you the main idea behind the proof. Okay. And in particular, I want to explain to you how everything is related to, RNets. Okay. Now, very importantly, you would like to identify a particular RNet. Okay, every RNet is characterized by the value R, right? RNet, right? So later we will choose this value of R very carefully. Okay, we'll choose it to be a power of 2. Why a power of 2? Because as well, you should still remember that we computed we computed 1 net, and then 2 net, 4 net, 8 net, 16 net, etc., etc., right? So every value R for which we computed an R net is a power of 2, right? So later on, we will choose this 2 to, we'll choose this power of 2, this 2 to the power of beta, okay? Very, very carefully, okay? This is something I will come back to later. But we will look at this 2 beta net. So if you think about the covering property of this 2 beta net, within this green circle, there must be a center, right? A center inside this 2 beta net, okay, to the power of beta net, right? So you want to choose this beta in such a way to make sure that this y, which is inside the green circle, and you can see the green circle represents a vicinity area of P star, right? So you want to choose the beta to make sure that this y is definitely, this y is definitely an out neighbor of P. Okay? So basically, this means the distance will have to be less than or equal to. Let's make it red here. This phi times 2 to the power of beta. Okay, so this phi is set here. Okay, so let's recall the story, right? So if this is true, and then by how we constructed the graph, how we generated the edges, and then that, you know, this y will have to be an out neighbor of p, okay? So very importantly, we have to argue that we can definitely find a very good beta, okay? So this is something I will worry about later, okay? So suppose this is what you have, right? So y is an out neighbor, but let's not forget that p plus has something very unique, right? So p plus has some very important property. So p plus is the best out neighbor of p, right? So it cannot be worse than y. You see what I'm saying? So basically, this says if you look at the distance of p plus and q, okay, so this distance cannot exceed the distance from y to q, right? So this is the meaning of the best out neighbor. Well, once this is true, and then I can resort to triangle inequality to write out several relationships. Okay, so the first one, you know, I will look at this p star and p plus. Okay, so p plus is the best out neighbor. Okay, so I will use q as the bridge to apply triangle inequality. Okay, so this will give me this inequality, right? Okay, now now I can utilize this inequality to work on this term here, right? So now this will become d yq, right? And then plus q p star. Okay. And then I will use triangle inequality to expand this term, okay? And this time I will be using p star as the bridge. Okay, so now I will have p star q and then another p star q from above, right? So this will give me two p star q, right? So now I can remove this term, right? So on the one hand, I can have, you know, this inequality. Actually, let's do one more step because I can write, you know, I can change this to the power of beta, okay, plus 2 times d p star q, right? So as you can see, if I can manage to find a y and also this beta as I hoped, and then this inequality will hold, right? So this is the first thing that will be useful. Now, on the other hand, if you look at let's start another string of derivation. So here, if you look at d p plus q, right? So once again, we can use this inequality here to say this is at most yq. Okay, so this is definitely true. And now if we use p star as the bridge to expand this, so this will become y p star and then plus, you know, p star q. Okay, correct, right? So once again, this term can be bounded by 2 to the power of beta. All right, so let's write it down here, 2 to the power of beta, and then plus d, and then, sorry, this is p star q. Okay, good. All right, so let's analyze these two terms a little bit. Okay, let's analyze these two terms a little bit, right? So first of all, intuitively, okay, if this is not very large, okay, so case one, all right, so let's write it down here. Case one, okay, if this p star q, so this is the exact nearest neighbor distance, right? If this is not very large, and then, you know, the whole thing will be, you know, will not be very large, okay? And this tells us that, you know, this p plus p star will not be very large, okay? So hopefully this will be small enough and this will be significantly, so this will be small enough for us to argue that this inequality holds. Okay, so if you can look at this inequality again, you can see that basically this inequality wants to argue that this term, okay, so this term here is not very large. Okay, so this is the first case. So once again, in this case, the nearest neighbor distance is not very large. Okay, so in this case, our goal is to argue that this is not very large. Okay. Now on the other hand, okay, so let's look at the opposite case, right? So this is so this guy is large. Well, if this is large, and then we will look at this inequality here. Okay, so if this term is quite large, with respect to 2 to the power of beta. Okay, so this term is quite large with respect to 2 to the power of beta. And then in this case, we will argue that, because we have an upper bound on the distance from P plus to Q, right? So we will argue that in this case, P plus is going to be a 1 plus epsilon ANN. Okay. So, so this gives you the main ideas behind the proof. And as you can see, in order to make the whole proof work, it's very important to resort to this 2 to the power of beta net. Okay, so next I'm going to give you the precise values of this alpha, this beta, and also I will argue I will argue for the existence of this magical walk. Okay. All right, so let's write out a proof formally. Okay, let's prove it. Okay, so so I'm going to introduce this alpha. Okay, so this alpha basically is the right hand side here. Okay, now let's write it down. Okay, so I have this. So D, P, and then P star. Okay, so this is alpha. Okay, this is alpha. All right, and because of this, and then this allows me to write, this D P star is bounded by 2 to the power of alpha. Okay, so intuitively, if you look at this distance here, P star, okay, if you look at this distance, it's roughly 2 to the power of alpha up to a factor of 2. Okay, so basically this is what it means. Okay. Now, formally, if you look at the lecture notes, you need that you know that you need to set the value of beta to be the maximum between 2 terms. Okay, so here. Okay, so this is alpha, which we just defined, and also this eta, right? So this eta is defined here, and as I was saying, this is basically log of 1 over epsilon. Okay. And you can see this is the maximum between this guy and 0, which means, if the first term here is negative, and then you should set beta to 0. Okay. Well, today in this seminar, I'm going to focus on the first case. Okay. I will assume that this is non-negative. If it's negative, and then it's actually an easy case. This is a corner case which can be handled separately. So I'm not going to spend time on that case. Okay, so this is something you can read, from the reference included in the lecture notes. Okay, so basically I will be assuming that beta is precisely alpha minus eta minus 1. Okay. All right, good. So you can see beta is an integer, right? And here we know that beta is precisely alpha minus eta minus 1. Okay. Now I can define this y. So this y, let's define it to be a point in the 2 to the power of beta net. Okay. And this is a center in that net covering P star. Okay, so we have, this inequality here, P star, and then Y should be less than or equal to 2 to the power of beta. Okay, so 2 to the power of beta, if I, rewrite it a little bit, and this is basically 2 to the power of alpha over 2 to the power of, sorry, this is 2. Okay, 2 to the power of eta plus 1. Okay. Yeah. All right. So next, very importantly, I have to argue that this Y is an outneighbor of P. Okay. So for this reason, for this purpose, there are two things you have to prove. Okay. So Y is not equivalent to P. Okay. So I will not prove this. Okay. I will just say it without proof. Okay. So not something very difficult, but something you have to show anyway. So I will not spend time on this. Okay. Again, if you want to know all the details, please read the reference I included in the lecture notes. Okay. But on the other hand, you also have to prove the following. Okay. So you want to argue that the distance between P and Y, you want to argue that this is at most phi times 2 to the power of beta. Okay. So because this is how we construct the proximity graph, and this, if this is true, and then by our construction, P must have an out edge to Y. Okay, so this is something we would like to have. Okay, so why do we have it? Well, now let's see, right? Now let's see. So we can, so let's say we write a little proof here. Okay, so we can apply triangle inequality. Okay, so this d p y. Okay, so this is, we can use p star as the bridge to apply triangle inequality. So now we've got this p star here, and then plus p star, then y. Okay, so p star. So we already know from here, as you can see. Okay, so this is bounded by 2 to the power of alpha. And then P star y, right? P star y, as you can see, this is bounded by 2 to the power of beta, right? And then you massage the terms a bit. Okay, so now this becomes alpha minus beta, okay, plus 1, right? So alpha minus beta is essentially just, is just eta plus 1, right? So this is something we can derive. Now, if you look at phi, right? So you look, this is exactly how phi is set. So now you know better, right? So this is actually the reason why this phi is set in this manner, right? So now you know that dpy is indeed less than or equal to, this phi times 2 to the power of beta. Okay, so now you should get convinced that, y is indeed an outneighbor of p. Okay, so what's the takeaway from this? The takeaway is that, you can see there is this beta value. This beta value should be selected in a very careful manner. Okay, and once you've got this, and then you can argue that this y is definitely an outneighbor of p. Okay, good. Now, if you understand this already, I'm going to erase this part. This is so this seminar is recorded. I'm going to release the video. So now you can, if you want to look at the proof again, you can play the video again. Okay, good. All right, very nice. So now we can apply so we can use the two inequalities here, right? So this is inequality 1, and here this is the inequality 2. Okay. And now we're going to consider two cases, all right, corresponding to the two cases here, all right? The two cases here. Now, case number 1. So in this case, we consider that, this d p star q is not very large. Okay, so this is not very large. Okay, so what do we mean by saying that this is not very large? So this is what we mean. Okay, so in particular, we set the threshold, this large, right? The large threshold to be the following. Okay, d p star q. This is bounded by, watch careful, right? This is 2 to the power of beta minus 1, and then 2 to the power of eta. Okay, eta, and then the whole thing minus 1. Okay, so this is the magic threshold. Okay, all right. Well, you don't have to get surprised, why this threshold is chosen, right? Because you already know the direction. If I say, this is the correct direction, and then eventually you will figure out this is the threshold. Okay, anyway, so let's look at this case 1. Okay, so if this is true, and now we can derive from 1 that, this p plus p star, so this is bounded by 2 to the power of beta, right? And then plus what? Plus 2 times 2 to the power of beta minus 1, and then 2 eta, and then minus 1, right? Okay, so let's work out the terms carefully. So this is 2 beta, and then we have 2 beta here. And then, right? So clearly, and this is just 2 beta plus eta, right? But beta is equivalent to this expression here, right? So this beta plus eta is nothing but 2 to the power of minus 1. Okay, you see what I mean? All right. So now you can see, indeed, we have this inequality. Okay, so you see, this part is alpha, right? Now let's indicate this here, right? So this is indeed alpha. You see what I mean? This is indeed alpha. So now if you look at this inequality, okay, so this inequality here, basically it says that if you take the log, and then you have, this is less than or equal to alpha minus 1. You see what I mean? Okay. And therefore, if you take the ceiling, because alpha minus 1 is an integer, right? So if you take the ceiling, this is still true. Okay. And therefore, for case 1, we have the inequality here. Okay. We have the inequality here. Okay. So this is what happens in case 1. Now let's look at case 2. Okay. Case 2 is the scenario where d p star q is strictly larger than this threshold. Okay, so I'm going to show you that in this case, this p plus, okay, so this p plus out, right? So p plus must be a 1 plus epsilon ANN of q, okay? So now, therefore, this will establish the claim in the lemma, right? So basically, either p plus is a 1 plus epsilon ANN of q, or this inequality will have to hold, right? So we have already seen that, in case 1, the inequality holds, and next, for case 2, I'm going to argue that p plus must be a 1 plus epsilon ANN of q. Okay, good. All right, now let's see. Okay, so if this is true, and then we will apply this inequality 2. Okay, inequality 2. So from 2, right? So if you divide this d p star q from both sides, right? If you divide both sides by that, and then what you get is this, right? P star q divided by, d p star q, right? So this is less than or equal to 2 to the beta over d p star q, and then what? And then plus 1, right? So I'm going to argue that this term here, okay, so I want to prove that this is less than or equal to epsilon. And then if I manage to do it, I complete my story, right? So this indicates that p plus is a 1 plus epsilon ANN of Q, right? Okay, now let's on this term, right? So this 2 to the beta divided by, d p star q, and we already know that, d p star q is quite large, right? So we know this is strictly less than 2 to the power of beta over 2 to the power of beta minus 1, and then 2 eta minus 1, right? So this gives us 2 over 2, to the power of eta, and then the whole thing minus 1, right? Okay. So finally, if you look at our choice of eta, okay, so you can apply the definition here, right? So definition here. So you plug in the value of eta, and then you will see that this is equivalent to epsilon. Okay. All right. So with this, I complete the proof here. Okay. So thank you for listening. Okay. Bye-bye.